All right, our lesson today is called integration by parts. Integration is doing an integral. So it's a technique for integrals, but I'm just going to review the techniques for derivatives and integrals so we know like kind of a mind map of what we need to think about when doing derivatives or integrals. The first thing for any problem would always be to try and rewrite and simplify. So same for integrals, always look to rewrite and simplify. Now, for derivatives, you might have to do a product rule, quotient rule, or a chain rule. For integrals, the only options that we have are to rewrite, simplify, or to do a U substitution. And a U substitution is basically the reverse of the chain rule idea. So you're looking for those parentheses and having more than an x inside the parentheses. That tells you to do U sub. Well, today we're adding another technique to integrals, and this is just a BC topic. So if you're an AB, you only have to worry about these two options. We have a third option for integrals, and that's called the integration by parts. And kind of the idea is with integration by parts is it's something where you can't do a U sub, you can't rewrite and simplify, and it kind of has a structure more or less of like a product rule. So it's kind of like the reverse of the product rule. So let me show you how it comes from the product rule. This is kind of like the proof of this integration technique, but you don't need to know, this is just for like a mind map, and then the proof that I'm going to show here is just to kind of show why this works, where it comes from, but it's not like you have to know this proof. So kind of the idea here would be that if let's say we were doing let's start with a product rule, since that kind of gives us integration by parts. So let's say the product is between u times v of the two parts. If I put a d over dx here, that means I'm going to take the derivative of this. And then I would have the derivative of this would be keep the u, but then derive the v. So u, and then times the derivative of v would be dv with respect to x, plus, and then for the product rule, now we would derive the u, so that would be du with respect to x times the original v. So this is just saying we're going to take the derivative of this, and here's the product rule. Well, now we're going to make it integrals, and so I'm going to add into all of these terms an integral, which means I should have like a times dx here, times dx here, times dx here. So I'm going to integrate everything to keep it balanced. And then here, what would happen is if you integrate with, take the derivative here, it would cancel out, like the dx's would cancel out, and you'd be left with just u times v again, what we started with. Over here, if we put the integral here, the dx's here cancel out, and you're left with just the integral of u times dv. We still would have an integral here because there's still a dv. And then here, these dx's would cancel out, and we would have the integral with, I'm going to rewrite, if these cancel out, instead of it being duv, I don't think that's the right order we should write it. It should be v and then du here. So we got two integrals here. Now, I'm going to rewrite this order, so it might not make sense to us now, but this is the order that we're going to find is useful. So what I'm going to do is subtract this term over to the other side of the equal sign. And then now what I'm going to do is just write this on this side of the equal sign. I'm just going to flip it to the other side and move this to the other side. So I'm just going to switch sides with the equal signs. Nothing complicated here, but I just want this term on the left side instead of on the right side. oops. Okay, so I switched the sides here. So now this from the left side is just rewritten on the right side. So here is our formula for the integration by parts. And I don't know who figured this out, that this would be helpful to us, because it doesn't look helpful. But what it's doing here is basically the two parts we're talking about are like these two pieces. And we're saying, so it's like we started with this problem, and this problem is equivalent to writing it like this. And then when you look at this, you'd think like, okay, if I start with this, how would this side be any better? But there's a way that we can take these parts, put them into these parts, and this more complicated looking side ends up becoming easier to work with. So for example, like this integral on the left, it's like, I cannot integrate that. Maybe by changing the things around to it's like this is equivalent to this, maybe by changing it to this integral, it's slightly different. Now it's v du. Maybe that version of the integral is able to be done and much easier to work with. So it looks like it's getting more complicated over here, but we'll see with the numbers plugged in and functions plugged in, it actually produces something easier to work with. So there's our formula. And in our notes, we already have the formula already typed in here, so we don't need to do that. And what we're going to do is like, we have to identify from our original problem over here, like this, it would be like our original integral, is first we'd have to realize like, can we rewrite and simplify? And if we can't, then we can't do anything. If we can't do a U sub, then we have to do integration by parts. So we have to pick the parts here. So one part we would call the U part, and one part we'd call the dv part. So here's the key. When you pick the U part, you want it to be a part that the U would be simpler when derived. And then we're gonna have to pick a dv part, and that, since it's already dv, is already the derivative, this one needs to be simpler when anti-derived. Now I'm gonna put here, sometimes it's simpler, or like I call it equivalent. What I mean by that is like, it's not simple, it doesn't look simpler, but just looks about the same like kind of idea when anti-derived. So we got to pick which parts U and dv, and sometimes we might pick those parts and get it wrong, and we might have to switch them and try something different. It's just the nature of integrals that you don't always get it right the first time. But here's a little like trick that people use to help remember which one should be the U and which one should be the V or dv. I don't use this. I just like to think about this, like how can I make it easier, and usually it works. But LIATE is the acronym. Starting with U, like the more easy way to do it is like, if you have a log, that's probably your U part. And then I is inverse trig. Gosh, I couldn't remember all this. I don't know why people use this so much. I just like to think about it this way. You know, that would be your next, that would be more likely to be U. A would be just like any kind of algebraic expression like x squared or something like that. Could be potentially either one, but usually it's going to lean towards the U. T would be the trig, is most likely going to be the dv part, like so if you have a sine, cosine, or something like that. And then lastly would be like the exponential, like e to the x or something like that. That's most likely going to be your dv. So again, I'm not memorizing these. I've never done that. And overall, this technique is going to look very confusing, especially at first. Like we haven't used it yet, but at first it's going to seem confusing. If we practice this regularly, this is going to be kind of a fun and good technique to use. So I'm going to go through next the samples below and kind of the process of how we can use this new formula here as an integration technique.